problem 7 for the test for review. Problem 7 says the plates of a capacitor are 5 meters by 3 meters and are separated by a distance of 30 centimeters. So you have this huge plate, capacitors, 5 by 3. They are separated by 30 centimeters. One plate has a charge of positive 10 coulombs and the other plate a charge of negative 10 coulombs. So you connected it to a certain battery and you gave this capacitor a certain charge. What is the capacitor's stored energy? So what happens is you connect it to a certain battery. Right now we don't know the voltage of the battery. And then you disconnect it and the capacitor is now charged. Okay, the capacitor is now charged and the top plate or one of the plates is 10 coulombs, the other plate is negative 10. It doesn't necessarily have to be the top plate or the bottom plate that is positive. Now, what is this capacitor stored energy? So the potential energy of a capacitor, there's 3 forms of the equation. We say half the charge of the one plate times the potential difference between the plates. A lot of times the potential difference, we don't write it as delta V. We just write it as V, which already means the potential difference. Now, since the capacitance of a capacitor is defined as the charge over the potential difference, therefore we know that the potential difference equals Q over C, and we also know Q is equal to CV. So to get the other forms of the equation for the potential energy, I can substitute Q equal to CV, and I get what? Half CV squared. Or I can substitute V is equal to Q over C, and then I get half Q squared over C. So in this problem, since I already know the charge is 10 coulombs, all I need to do is calculate the capacitance of the capacitor, right? So the capacitance of the capacitor is equal to C is equal to A E0 over D, the area of the one of the plates, times the E0, the electrical permittivity of space, divided by the distance. So the area is equal to 5 times 3 times E0, 8.85 times 10 to the minus 12, divided by the distance between the plates, which is 30 centimeters. Change that to meters and you'll get 0.3 meters. Okay, so let's multiply all of that out. 442.5 times 10 to the minus 12 farads. The other way to express that is you can say 442.5 picofarads. 442.5 picofarads. Pico means 10 to the minus 12. Or you can express that as if you go back 3 spaces, you have 1, 2, 3, then there'll be 10 to the minus 9. So it'd be 0.4425 nanofarads. Because if you go back 3 spaces, you get 10 to the minus 9, and 10 to the minus 9 abbreviated means nano. Okay? So now we're going to take that and we're going to put it into the equation for the potential energy. So 10 squared divided by 442.5 times 10 to the minus 12, since that's on the bottom here. So then you have 442, then 2 goes, this one becomes 100, 2 goes into 150 times. So 50, so it becomes 1.13 times 10 to the power 11. Okay, so, and that is the answer, 1.13 times 10 to the 11, because 50 divided by 442 was 0.113, the 10 to the negative 12 went on top, become 10 to the 12, and if you go 1 to the right, and you can make this 10 to the 11th joules. What happens if you insert a dielectric in there? Okay? If it's not connected to the battery source still, let's say the capacitor is by itself, okay? And if you insert the dielectric, the dielectric constant kappa is 2.5, what happens to its capacitance? Its capacitance is now kappa A is 0 over D. So the capacitance goes up by a factor of kappa, 2.5. So remember, the capacitance used to be 442.5 picofarad, 442.5 picofarad. Now I'm going to multiply that by 2.5, and the capacitance is going to be really big. It's going to be 1106.25 picofarad. Now, if since the charge is going to stay the same, it's not connected to the battery source, there can be no flow of charge. So what's the potential energy going to be? The potential energy final, well, I'm keeping the charge the same, I'm increasing the capacitance by a factor of 2.5, right? That means the potential energy is going to decrease by a factor of 2.5, right? Because the capacitance is increasing by a factor of 2.5. So the potential energy final is the potential energy initial over 2.452 times 10 to the 11th, or 4.52 times 10 to the 10th joules. Okay, and that is the answer, 4.52 times 10 to the 10th joules. So since the potential energy has dropped, what does that mean? Well, that means as I'm putting the dielectric in there, the dielectric actually gets sucked in, and the loss of potential energy shows up as kinetic energy in the dielectric. When the dielectric is here, it has some velocity. So that means actually it can kind of pass that point and start making oscillation motion. So that means the system likes to have the dielectric, it likes to always be at a lower potential energy, and the dielectric would make some kind of harmonic motion there until it eventually comes to rest. Okay? Now what would happen differently if while I'm trying to put in the dielectric, the capacitor is still connected to its original voltage source? What is the potential energy now? Okay? Remember, the potential energy equation is U is equal to half Q squared over C, half QV, or half CV squared. The original voltage is equal to what? V is equal to Q over C. Right? So it's better in this kind of a case, it's better to calculate what is the original battery that was connected to the capacitor. The charge was 10 coulombs and the capacitance was 442.5 picofarads. So that's 10. And then on the bottom I have 10 to the minus 12, which goes to the top and becomes 10 to the 12th. Right? So the voltage source that this capacitor is connected to, that is causing 10 coulombs of charge, is a huge voltage source. So times 10 to the power 12. So that's going to be 2.259. This one goes over. 2.259 times 10 to the 10th volts. The form of the potential energy equation that I have to use is this one now. U is equal to half CV squared. U initial is still the same, half C initial, V initial. That's going to be 1.13 times 10 to the 11 joules. U final is going to be what? Half C final, V final squared. Now, since I have it connected to the same voltage source, the V final is the same, right? So the V final is the same as V initial, so I can use this one. What's C final? C final is this one. The capacitance went up by a factor of 2.5, right? So I'm going to have half. Now, you're going to have 2.25 times 10 to the power 10th, 11 joules. Now, what is that equal to? 2.82 times 10 to the 11 joules. What's the basic gist? Well, actually, that ends up being 2.5 times the potential energy of the initial potential, U final. If you do 2.5 times 1.13, what would you get? 2.5 times 1.13. You get 2.82 times 10 to the Now if you multiply the 11th, you get 11 joules. So what is our conclusion? So if the power source is not connected while I'm putting the dielectric in, the charge stays the same, the capacitance increases, the potential energy decreases. If the power source is connected while I'm putting the dielectric in, here's what happens. In order to keep the same voltage, the power source has to send more charge there. What does that mean? Well, that means in this case, I'm going to have to do work in. The capacitor is not going to want to receive the dielectric. So in order for me to put the dielectric in, I'm going to have to push it. I'm going to have to push it. I'm going to have to push it in order to get the dielectric to go in, because the battery is going to have to supply more charge to the system in order for that to occur. So depending on whether the battery is connected or not, either it goes in by itself and it changes to kinetic energy, or I'm going to have to push it in order to raise the potential energy of the system. Okay? Thank you.